Here we will discuss the concept of the inner product, which is a generalization of the dot product seen in multivariable calculus and linear algebra. We will also introduce orthogonality and the norm of a vector. Recall the idea of a dot product of two vectors. This was a way of taking two vectors and getting a scalar that represented something about the relationship of those two vectors to each other. You can think of the dot product as a function that has as its input two vectors and as its output a scalar. This idea can be generalized to obtain many such functions on any vector space, and these are called inner products on V. This is a function that takes two vectors from V and returns a scalar. However, in order to be an inner product, these functions have to have a few more properties. First, the inner product must be symmetric, so u times v must be the same as v times u. Second, it must be linear, in the same way that the product of two numbers is linear. So scalars can be pulled out of the product, and a distributive property exists over addition. Finally, the inner product of a vector with itself must be non-negative, and the only time that the inner product of a vector with itself can be zero is when the vector is zero. As an example, let's consider a modified dot product on R2. So let's consider these two vectors, u and v, where u is 1, 2, and v is negative 3, 1. And we define an inner product on R2 by this following rule right here. We can see this is similar to the dot product, but decidedly different. And if you are unsure if this inner product function satisfies the three properties above, then I really suggest you take a minute and try and prove it to yourself. It's not terribly difficult. Using this inner product, we see that the inner product of u with v is going to be 10. And this example shows that many inner products can exist on the same vector space. Usually when we choose a vector space, we also set an inner product with which to work. There's often a typical inner product on vector spaces, though. And in this class, we will work mostly with function spaces. Remember, those are vector spaces that involve functions, such as the continuous functions or k-differentiable continuous functions. The L2 inner product is the common one to use for function spaces. It is defined by multiplying two functions f and g together and then integrating across the domain, AB. So we see again that the inner product takes two vectors, or functions in this case, and outputs a scalar. In this case, we use integration to turn those two functions into a scalar. For example, let's take two functions in the space C0, 1. So continuous functions defined on 0, 1. F is going to be sine of pi x, and g will be cosine of pi x. By multiplying and integrating these two functions, we see that the L2 inner product is 0. This is actually quite interesting and relates to an idea that we'll talk about next. Recall that if the dot product of two vectors in R2 or R3 is 0, then those vectors will be perpendicular to each other. Here we see an example of two vectors in R2. Their dot product can easily be calculated and shown to be 0, and we can plot them and see that they are in fact perpendicular. Well, while the geometric idea of perpendicular does not really extend to other vector spaces, especially if we're talking about function spaces, many of the algebraic properties of perpendicular vectors does. And so therefore, we use a different terminology. For a general vector space V, we say that two vectors are orthogonal if their inner product is 0. So two perpendicular vectors in R2 or R3 are also called orthogonal. But in the more general sense, where perpendicular doesn't really make a whole lot of sense, we use the terminology orthogonal. All the geometric properties of perpendicular vectors translates to orthogonal vectors. And the one that is really of interest to us right now is the fact that if two vectors are orthogonal to each other, then they will be linearly independent. Next, we will define the norm of a vector. This is very analogous to the absolute value of a scalar and exactly the same as the norm that you learned about in multivariable calculus and linear algebra. The norm is a function from a vector space to R with the following properties. First, the norm of a vector must be non-negative. Second, scalars can be taken out of the norm, but when you do take a scalar out of a norm, it gets put into absolute value. And finally, we have the triangle inequality, which is exactly the same type of triangle inequality that you know from the absolute value. So in summary, a norm is simply a function that assigns to all vectors a scalar, a real number. When an inner product is defined on a vector space, we can compute the norm using the inner product. The norm of a vector u is defined to be the square root of the inner product of u with itself. We can now see why the inner product of a vector with itself must be non-negative, because otherwise the square root would be complex. The basic idea of a norm is that it defines the length of a vector. In R2 and R3, this makes a lot of intuitive sense, since we can simply measure the vector with a ruler. However, this can be extended to consider the length of other vectors, such as functions. For instance, we can determine how long the function cosine of pi x is in the space C0, 1. Using the inner product, we take the square root of the integral of f squared, and we see that the function has length 1/2. All right, so we can define some sort of concept of length for functions. However, we often don't really want to know the length of a function. For instance, in our situation, we don't usually want to know how long the solution of a differential equation is. What is of interest, though, is the distance between two functions, how different two functions are from each other. And this can be calculated by considering the norm of f minus g. You can see how this might be interesting when approximating solutions with an algorithm. You might want to know how close your approximation is to the exact solution, and by examining the norm of the approximate minus the exact solution, you can determine this. When we use the L2 norm to calculate the distance between functions, we often use the term mean square. So for instance, we might say that two functions are close in the mean square sense, if they are close using the L2 norm. For an example, let's take these two functions f and g. Right? Notationally, they really don't look very similar at all, but by considering the norm of f minus g, we see that they are relatively close to each other in the mean squared sense. Now, this does not mean that the functions are necessarily close at each point in the domain. Here we see a plot of the two functions and note that they are often much farther away from each other than their mean squared distance, 0.00694. The norm simply gives us the distance of the two functions on average over the interval.